Hi, today we are going to be learning about finding the volume of solids with known cross sections. Our first problem says find the volume of a solid whose base is enclosed by the circle x squared plus y squared equals 9 and whose cross sections taken perpendicular to the x-axis are, for part A, squares. We'll just focus on that to start. Okay, so this might seem kind of strange to find a volume of this solid because you may have a difficult time picturing it, and that's okay because you don't actually have to be able to picture it to find the volume. We have a formula for the volume of a solid with a known cross-section, and this is one of your note cards. The volume is going to be equal to the integral from A to B, and A is the leftmost x value, and B is the rightmost x value for your base of your solid. And then you're going to write a formula, an algebraic expression for the area of the cross-section in terms of x. So this will be like an f of x function, but it's an f of x function that gives us the area of the cross-section. And then we'll have dx. So for this first one, we want to go ahead and begin by drawing out the base of the solid. So I'm going to make a little coordinate plane right here, and it says that the base is a circle with this equation, x squared plus y squared equals 9, which we know means that the center is at the origin, and the radius would be 3 because x squared plus y squared equals r squared, the radius squared. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Here is the base of my solid. So it sits upon a circle. Can you think of any shapes that you've seen maybe in geometry or something previously where it sits upon a circle? Maybe like a cylinder or a cone, okay? But the problems that we're going to be doing in this unit are not going to be volume problems that you have found the volumes for previously. It's not going to be something you could have done in geometry. So this one is one where the cross section's taken perpendicular to the x-axis. So that means like if I come in and karate chop it perpendicular to the x-axis or parallel to the y-axis, and I open it up and look at it, I'm going to see a square. So I happen to have a model of this particular example, and I'm not going to have this for all of them, but I do for this one, to help you see what we're talking about. So this right here is the solid that has a base of a circle, and when you open it up, you can see the cross sections are a square. There's your square. So this little darker piece of wood is like the cross section. You can take it out and look at it. And then here's the other piece. So it has these two ridges that go around the shape. Those are like your upper vertices of your square. And so the square on the very bottom is super tiny, and then it gets bigger and bigger and bigger and bigger until it reaches its height and then goes down. So that's what our first shape that we're finding the volume of looks like. So we're going to use this formula, and we know that our volume is going to equal the integral from the leftmost x value here is -3, and the rightmost x value is +3. Now, we have these squares, and the squares are the cross sections, something like this. See if I can draw a parallelogram-ish rhombus looking thing to try to make it look 3D. So basically, the area is going to be the length times the width, but we need this expression in terms of the variable x. Right now, if you take a look at this point where the vertex of my cross section would be, it's like it's at xy. So the base of my square would be y units up from the x-axis and another y units down from the y-axis. So it's like the side length, let me come over here, the side length of the square is 2y, okay? But we do not want it in terms of y. We want it in terms of the variable x. So what we're going to do is take this circle equation, isolate y so that we have an expression for y in terms of the variable x. So I'll start by subtracting x squared from both sides. And then I'm going to take the square root on both sides. And I really only need to take the positive square root, not the negative square root, because I'm talking about the length of a square, the side of a square. So we're going to say the side of the square is equal to 2 times, in parentheses, we'll do a substitution here, the square root of 9 minus x squared. Okay? So now that I have the side length of the square, I need to come up with a formula for the area of the square. So to find the area of a square, we just take the side length and we square it. So it'll be 2 square root of 9 minus x squared quantity squared. So let's go ahead and square that. If you square that, 2 squared is 4, and then the square root squared means it's going to come out of the square root, but remember there's an assumed set of parentheses around every root, around the radicand, the number under the radical. So that stays in parentheses because this 4 will have to distribute across the parentheses. So the area will be 36 minus 4x squared. This formula represents the area of the cross section at any given x value on our solid. So we are going to integrate that, 36 minus 4x squared dx. Now, it's possible that you might be asked to do this without a calculator, but at this point in the year, we have done a lot of problems without a calculator, a lot of integration problems, and today's focus is more on setting up the integral that you would find the volume with. So I'm going to use the calculator to find this, but for your homework, you probably ought to practice doing a few of them without the calculator just for practice. So this would be a pretty easy one to do without a calculator. We're going to go alpha, window, option 4 for function integration. Lower limit is -3, upper limit is 3. And then we're going to type 36 minus 4x squared as our area of the cross-section function, dx. And now we have 144 is the volume of this very interesting solid. Pretty cool, huh? All right. The next one is with the same setup, base of a circle, x squared plus y squared equals 9, and the cross sections this time are going to be equilateral triangles. So where I had squares coming up here, I had this square cross section on this one. Now I'm going to have an equilateral triangle for my cross section. So I've got the same base, 3, 3, -3, -3. Here's my circular base. But perpendicular to the x-axis, I have this line that makes up the base of an equilateral triangle. So my cross section is an equilateral triangle this time. How do you find the area of an equilateral triangle? Well, the area of the triangle formula is 1/2 of the base times the height. So that's what we're going to have to put in to our integral. -3 to 3 is still the leftmost x to the rightmost x for my integral. but I need to come up with an equation which gives me the area of this triangle for any x value in terms of the variable x, okay? Notice that the base of my equilateral triangle is the same as the base was of my square. Y units up from the x-axis, y units down from the y-axis, for a total of 2y. So I'm going to say the base is equal to 2y, and we determined that for this equation, y was equal to the square root of 9 minus x squared. So I'm going to replace the y with the square root of 9 minus x squared. But now I need the height. In order to figure out the height, I'm going to use some geometry, okay? So let's take a little trip down memory lane to geometry class. I know that's been a while. This is an equilateral triangle, okay? That means it's a 60, and another 60 degrees. I know that the base of this equilateral triangle is 2 square root of 9 minus x squared, but I want to know the height. So if I draw the height on here, there's my 90-degree angle. This makes a 30, 60, 90 triangle. And the short leg of the 30, 60, 90 triangle is going to be half the length that the base of the equilateral triangle is. So that's half of 2 times the square root of 9 minus x squared, which means this side is just going to be the square root of 9 minus x squared. So how do you find the height then? Well, if you'll remember your properties of 30, 60, 90 special right triangles, you take your short leg, which the short leg here is equal to the square root of 9 minus x squared, and you multiply it times the square root of 3 to find the long leg. Does that sound familiar? So the long leg, which is equal to the height, is going to be the square root of 3 times the square root of 9 minus x squared. Okay, and then the hypotenuse is the short leg doubled, which notice is 2 times the square root of 9 minus x squared, which was the length of the base, and we said all of these sides are the same, so that does make sense. All right, so I have the height and I have the base. So I'm going to do 1/2 times the base times the height for my area of my equilateral triangle expression, which is what I'm integrating to find the volume of the solid. So 1/2 times 2 is equal to 1. I could pull the square root of 3 out in front of the integral. And then the square root of 9 minus x squared times the square root of 9 minus x squared is like squaring a square root. So that's going to come out of the square root. So it'll just be 9 minus x squared dx. So you could integrate this by hand very easily and then just multiply times the square root of 3 at the end. But we'll do this one in the calculator again. So alpha window, option 4 for function integration. I have -3 for my lower limit of integration, 3 for my upper limit of integration. Oh, I forgot to multiply by the square root of 3 out in front. Had to insert that. 9 minus x squared is my integrand dx. So what does this give us? It's a decimal answer, of course, because we're multiplying times the square root of 3, which is an irrational number. So we've got 62.35. That's going to round to 4 after that because the next number is an 8. And we always round to 3 numbers after the decimal place unless explicitly told otherwise. And guess what? I do have a model of this shape in case you were wondering what it looks like. Notice we did the whole problem without worrying what it looked like, but I am missing a piece of it. This is what it looks like. It's a circle on the bottom. See, I'm missing this cross-section piece that comes out. And then it's got this ridge, one ridge, where that upper vertex of that equilateral triangle is. But when you open it up, there's your equilateral triangles for your cross sections. And it just goes all the way around like that. Interesting, huh? All right, that's the last one I have a model for. So we're not going to keep drawing these or visualizing these each time, but that's okay. Because we can just look at the base and one cross section and we'll be able to figure it out from there. Number 2, part A. Find the volume of the solid whose base is the area enclosed by the line y equals negative x plus 6. Okay, I'm going to go ahead and draw that. This is a y-intercept of 6. 1, 2, 3, 4, 5, 6. Slope of negative 1. So down 1, right 1, down 1, right 1. It's going to go all the way out until it hits 1, 2, 3, 4, 5, 6 over here. The y-axis and the x-axis. So this is my base, this little right triangle that you see here. The cross sections taken perpendicular to the x-axis are squares. So here is a side length of my square. Okay, it goes to the point x, y on my linear function. So my volume equation is going to equal the integral from leftmost x, which would be 0, to rightmost x, which would be 6, because that's the x-intercept of this linear equation. And we need to come up with an area formula for the base of our square. I mean, not the base of our square, for the cross section, which is our square, coming up like this. So notice the bottom of my square starts at the x-axis and goes up to this y coordinate. That means the side length of my square is y units. That's going to change as I move along the line, but it's always whatever the y coordinate is, okay? We need this in terms of the variable x. So since y is equal to negative x plus 6, I'm going to take out the y and replace it with negative x plus 6. That's the side length of my square. Now the area of my square is going to be the side length squared, quantity squared. So I'm going to integrate the quantity negative x plus 6 squared dx. Now, if I was doing this by hand, I would FOIL that out and combine like terms so that it was simplified before I started doing power rule backwards to integrate. But I'm going to do this one in the calculator. So I'm going to go alpha window number 4 for function integration. 0 to 6 are my limits of integration. I'm going to add a parentheses, negative x, plus 6, close parentheses, squared, dx. So this equals 72. The volume is 72. All right. Part B. What if the cross sections were isosceles right triangles with the base on the xy plane? All right, so same base, but we have a different shape cross section this time. We're talking about an isosceles triangle with its base on the xy plane. So remember from the formula of the area of a triangle, the base times the height divided by 2 gives us the area, and the base of an isosceles right triangle would be one of the 2 congruent legs, because the base and the height are going to be congruent to each other. So our side length is still, well, let's say the base of our isosceles right triangle is still that y coordinate, which means it's going to equal negative x plus 6. The height is also going to be negative x plus 6, since the base and the height are congruent on this isosceles right triangle. So the area of the triangle is going to be base times height divided by 2, or 1/2 times the base times the height, which we could write easier just by squaring negative x plus 6. So the volume is going to equal the integral from leftmost x, which is still 0, to rightmost x, which is still 6, of 1/2 times negative x plus 6 quantity squared. Oh, I forgot the dx. Okay, so that's what I'm going to put in the calculator. Anybody want to guess what the answer is going to be before I do that? Alpha, window, number 4, 0 to 6. I'm going to put 0.5 instead of 1/2. Negative x plus 6 close parentheses squared dx. It equals 36. How is this answer related to the answer to part A? Oh, it's exactly half. Why is that? Notice these integrals are exactly the same, except for this has a 1/2, which could have been moved out in front of the integral. Then you could have evaluated the same integral you had in part A, and then just taken that answer, 72, and multiplied it by 1/2 or divided by 2, which would give you 36. It kind of makes sense too if you had square cross sections and then you cut them each in half diagonally, that it would be half the volume. Okay, the next one, part C, is with semicircles, okay? So we've got the same base that we've had on all of these, 6 here, 6 here, this right triangle base. Now, this time we have semicircles for the cross section. So the diameter of the semicircle coincides with what the base of our isosceles right triangle was, or the side of our square was. So that's your y coordinate, but we'll just go ahead and write it as negative x plus 6, since we know that y is equal to negative x plus 6. So how do you find the area of a semicircle? Well, it's 1/2 times the area of the circle. Area of the circle is pi r squared. So 1/2 pi r squared, or pi r squared divided by 2. So we need the radius, and the radius is half the diameter. So 1/2 of negative x plus 6. So the area of the semicircle will equal 1/2 pi times the radius, which is 1/2 negative x plus 6 squared, quantity squared. Watch out on this. There's 2 halves, one for the radius and then one for the area of the semicircle. And there's 2, wait, is there 2 squares? No, I lied. There's only 1 squared. What are you doing? 1/2 pi times the radius. Oh, I know where I'm thinking. The square needs to be around the 1/2 and the negative 1/6. So like you've got to put this in brackets and then square it. Let me write that a little more clearly. I apologize. 1/2 pi times the radius, which is 1/2 of negative x plus 6, quantity squared. Is that better? Okay. So that is what we are going to integrate. And I definitely would simplify that if I was doing it by hand. If I was doing it by hand, I would square 1/2 to get 1/4, multiply it by 1/2 here, which would be 1/8, and pull the 1/8 pi out in front of the integral symbol. And then I would FOIL out the negative x plus 6 so that I could do power rule backwards easily. So here my volume formula is going to be the integral from 0 to 6 of 1/2 pi times 1/2 times negative x plus 6 quantity squared dx. All right, let's see if I can enter this in the calculator without making a mistake. I think I would rather integrate this by hand because this is too much button pushing. 0.5 pi times 0.5 times negative x plus 6. Close the parentheses for the negative x plus 6. Close the parentheses that holds the whole radius with the 1/2 multiplied by it, and then squared. dx. Yay! So this should equal 28.274. If this was a no calculator problem, like I said, you would pull out your constants in front of your integral and then multiply them back at the end, so it would be in terms of pi. You wouldn't get your decimal answer. It would be an exact answer. All right, moving along. Problem 3. The base of a solid is the region in the first quadrant bounded by the y-axis, the graph of y equals the inverse tangent of x, the horizontal line y equals 3, and the vertical line x equals 1. For this solid, each cross-section taken perpendicular to the x-axis is a square. What is the volume of the solid? Look at this. This is a multiple choice problem. The answers are all decimals. This was intended to be done with a calculator for sure, okay? So let's go ahead and go into our calculator and type this function they gave us, y equals the inverse tangent of x. So y'all know you've got that inverse tangent when you hit second and then the tangent of x. And we are in radian mode, and we're always in radian mode in calculus class unless explicitly told otherwise, which almost never happens. So I'm going to hit graph. So here is this inverse tangent function that you remember from pre-cal. And then we also have y equals 3 is another boundary line. So I'm going to go y equals, for y2, 3. So we want the region bounded by the y-axis, so this up and down, the inverse tangent, the line y equals 3, and the vertical line x equals 1. And x equals 1, that's going to make it really small. So I'm going to try to sketch this over here. X and y axis. Here's my little inverse tangent curve. And then the line y equals 3 is up above it. And x equals 1 is right here-ish. Kind of missed it. So here's 1, here's 3. So we're talking, let me get my little highlighter. We're talking about this region right here. This is the base of the solid. So for my volume formula, the integral is going to start at the y-axis, which of course is where x is 0, so the leftmost x is 0. And it goes to the line x equals 1, so the upper limit of integration will be 1. Now, we have a square cross-section, so my square sits with a base that extends from the function y equals 3 to the function inverse tangent of x. So this vertical distance can be measured by taking the upper function minus the lower function. And then you will see this is quite common on these problems. So I'm going to go upper function is 3 minus lower function is the inverse tangent of x. That's the side length of my square. But remember, we're integrating the area of the cross section, the algebraic expression representing the area of the cross section of our solid. So if this is the side length and the cross sections are squares, I'm going to take the side length and square it for the area. So that's what I'm going to integrate, because the side length is 3 minus the inverse tangent of x, and the area is that quantity squared. So I'm going to go back to my home screen and my calculator, and go alpha window, option 4, function integration, integrating from 0 to 1, parentheses, 3 minus second tangent for inverse tangent of x, close the parentheses on the argument of that inverse tangent, close the parentheses that holds the 3 minus the inverse tangent of x, and square that for the area of the square, dx. So let's see if our answer's here. 6.612. Yep, that's B. 6.612. All right, number 4. Let R be the shaded region bounded by the graphs of y equals the square root of x. So I know the square root function goes through the origin and curves up like this. So this is the upper function here. And y equals e to the negative 3x. So that's the one that's going down because of the negative exponent. And the vertical line x equals 1 as shown in the figure. The region R is the base of a solid. For this solid, each cross section perpendicular to the x-axis is a rectangle whose height is 5 times the length of its base in the region R. Find the volume of this solid. So I have rectangles. So the base of the rectangle is perpendicular to the x-axis sitting on this region R. So it's the distance between the upper function and the lower function. The upper function is the square root of x, and the lower function is e to the negative 3x. So upper function minus lower function gives me the base of my rectangle. The height of my rectangle is 5 times the length of its base. So just take 5 then parentheses, and then write the base again. So that means the area of the rectangle is just base times height. So it's going to be 5 times this times this. These are the same, so I'm going to just put squared on it. 5 times the square root of x minus e to the negative 3x quantity squared. So the volume of this solid is going to equal the integral from, oh, and this is a calculator problem, just like the last one was a calculator problem. Leftmost x value. This is what made me think of it. This intersection point, we do not know. We need to know the coordinates of that intersection point because the x value is the lower limit of integration. The y value, the upper limit of integration is 1 because it's going to the line x equals 1 on the right. So 1 is going to go up here, but we don't know what that lower limit of integration is, so we need to find it. So I'm going to put in my calculator y equals the square root of x for my upper function, and y equals e to the negative 3x power for my lower function. And I'm going to graph them. But when I graph them, I want to find the intersection, and it's super close to the origin. Notice the scale on this graph is 1 and 1. It's like 0 to 1. So I'm going to go to my window and make my window here match the window I see on my paper. So my x-min is 0, and my x-max is 1, and I'll count by 1/10. Y-min, 0, Y-max, 1, and I'll count by 1/10 there. So this should look more like what I see on this picture on the paper. So I'm looking for this x-coordinate of the intersection. So I'm going to hit second, then the trace button for the calculate menu. I want to choose option 5 for intersect, and it says first curve question mark. It just wants you to arrow close to where the intersection point is that you're trying to find on that first curve, because it can only find one intersection point at a time, and it can only find an intersection between 2 curves, and you could have like up to 10 in here. So I'm going to press enter here, then it says second curve question mark, and you can see now it's moved to the e to the x curve. So yes, I'm going to hit enter again. Yes, we do not care. Press enter a 3rd time. And now it tells us the intersection is 0.2387341 and 0.4886047. Now, the most common AP Calculus test error is premature rounding. This answer is not the final answer to the problem. You cannot round it off and use the rounded off answer to calculate your final answer of the problem. You have to use all the digits. The good news is your calculator will remember them for you. If you go to your home screen, second quit, and you just type this button X like you were entering an X in your Y equals and press enter, it saves all those digits, 2.2387341. Actually, it goes a little further, 293 than what we had written down. So it will use all those digits on your home screen now anytime you type the X button until you use your calculator to calculate a different X value. So we're going to go, I can write it down here, 0.239. I can write it down as the abbreviated, but I cannot use that abbreviated, that rounded off answer to do the computation, because it will produce error in my answer and it will make me have a wrong answer for the AP exam, which is bad, especially if I knew what I was doing. So then we've got 5 times the square root of x minus e to the negative 3x quantity squared. I just copied my formula for the area of this square cross section in terms of the variable x dx. And this is what I'm going to get my calculator to do for me. So I'm going to go alpha, window, option 4 for function integration. Lower limit, I'm going to type the x because it remembers x from your computing the intersection point on your graph. Upper limit 1, and now I'm going to go 5 times, I could actually, because see in my y equals, I still have the square root of x and I have e to the negative 3x. I know these aren't very lengthy functions, but I can actually just pull those in from that graph menu since I already typed them once. I can go alpha trace y1, which is my first function, square root of x, minus alpha trace y2, which is my second function, close parentheses, squared dx. And this x is different. It will not pull that number in for the dx. It's using the x as the independent variable there. I know, it's amazing. Now we're going to press enter, and it gives us the answer, which is 1.554. And that's a done deal. Okay, going on to the next problem. Number 5. I believe this is the first fully done AP problem you're gonna have done with me this year. We finally learned enough calculus to do on all parts. It says, let R be the shaded region in the first quadrant enclosed by the graphs of y equals e to the negative x squared, y equals 1 minus the cosine x, and the y-axis as shown in the figure. Find the area of the region R. Guess what? We did this problem in our notes last time. So I'm going to skip it because I already gave you this problem. Look back. We did it. All right, B. The region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is a square. Find the volume of this solid. Okay, so this is the base of the solid. We're going to do a volume problem. So we're going to integrate from leftmost x, which is 0, to rightmost x. And we found this intersection point last time in class because it was part of this part that we just did. And it was x equals 0.941944408. We did that with the calculator using the intersection feature. So that's my upper limit of integration, 0.941944408. So we're going to have to look at the cross-section being a square. So I've got upper function minus lower function is the base of my square. So that's going to be e to the negative x squared minus, in parentheses, 1 minus the cosine of x, because this negative will distribute to the 1 and to the negative cosine. So that's the upper function minus the lower function, which is the side length of my square. And then to do the area of the square, I will square the side length. And then I'm going to have a dx. And this is a calculator problem. So we're going to use the calculator. I'm going to go ahead, because I know what's ahead, I'm going to store this number in my calculator so that I can use it on the other parts as well. So I'm going to say 0.941944408, typed it in, and then I'm going to hit the STO button, which is the store button on the calculator, and I can store it as any letter I want. I'm going to store it as H for Heiss. You can store it as your initial if you want. So the H is if you hit the green alpha button and then the caret button next to pi is the H. So now it says store that as H, and I'm going to press enter. So now anytime I hit alpha H, it's going to have that number stored until I clear my memory in my calculator or store over the top of that one. So I'm going to go alpha, window, option 4 for function integration. Lower limit 0, upper limit alpha H, and then I'm going to go e to the negative x squared minus parentheses 1 minus cosine x. Close the parentheses on the argument of the cosine. Close the parentheses around the 1 minus the cosine of x. And then there was already a built-in parenthesis for my integrand, dx. Enter. Uh-oh. Something's wrong. This is not the right answer. What did Mrs. Heiss do? Oh, I forgot the square. I just integrated the side length. I didn't square it. And see, this is why you need to check your answers when you're doing your homework so you can make sure that you're doing them correctly and notice if you've got mistakes and fix them so that you become less prone to those types of mistakes. It also helps when you're doing a multiple choice question and you look and your answer's not there. Uh-oh, this is still not good. Boy, I wish you were here with me in class so that you could tell me what I'm doing wrong, because y'all always do. All right, I'm just going to start over. Alpha window, number 4, 0, and I'll just type it in, 0.9419440.8. And then I've got e to the power of, oh, I better put a parentheses here. E to the power of negative x squared and I'm going to go minus 1 and I'm going to go plus cosine of x so that I distribute the negative, one less pair of parentheses I have to use that way. And then I'm going to close the parentheses and hit squared and go dx. There, it gave it to me. 0.461. Persistence pays off. Okay. Now, C. The region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is a rectangle where the height of the rectangle is half the width. Find the volume of this solid. So the base of my rectangle is equal to the same thing as the base of the square was. E to the negative x squared minus 1 plus the cosine of x. The height is half that width. So the height is 1/2 of the base. So the area of the rectangle is the product of these two, base times height. So it'll be 1/2 times e to the negative x squared minus 1 plus the cosine of x squared, because this is the same as this. So you multiply them, it's going to be squared. And now we just write our volume equation, which is going to be the integral from 0 to the 0.9419440.8 number. 1/2 of e to the negative x squared minus 1 plus cosine x squared dx. Notice that this is the exact same thing that we integrated on the last problem, except for there's a 1/2 in front. So guess what I'm going to do? I'm going to take this answer I just got and go times 0.5. 0.231 is the answer. All right. D. The region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is a semicircle whose diameter lies on the region R. Find the volume of this solid. So, our diameter of our semicircle is the same thing that our base of our rectangle was. E to the negative x squared minus 1 plus the cosine of x. And the radius is going to be half of that. So let's scoot this down. Half of e to the negative x squared minus 1 plus the cosine of x. So the area of the semicircle is going to be half of the area of a circle, 1/2 pi r squared, so 1/2 pi times the radius, which we just wrote down, 1/2 times e to the negative x squared minus 1 plus cosine of x squared. So 1/2 pi r squared. And then we are going to find the volume, which is the integral from 0 to that 0.9419448 of our area, 1/2 pi times 1/2 times e to the negative x squared minus 1 plus cosine x squared dx. All right, this is what I have to work out, and this is the last one. So I'll type this in the calculator, see if I can get it right. Lots of button pushing. Alpha, window, number 4 for function integration. 0 to 0.9419448. And then my integrand is 0.5 times pi times, in parentheses, 0.5 times another parentheses, e to the power of negative x, negative x squared minus 1 plus cosine x. Close the parentheses on the argument for the trig function. Close the parentheses on the e to the negative x squared minus 1 plus cosine x. Now close the parentheses that holds the 1/2 with that for the whole radius. Square it. There's automatically a closed parentheses for your integrand, and then dx. Enter. Oh, I have an extra decimal. In the upper limit of integration, I hit decimal instead of 0. Fun. Oh, another mistake. Oh, this is not right. Insert a negative. Okay. There, finally, we got it. 0.181. Now, I strongly want to encourage you to definitely practice typing all of these in your calculators when you are told to use a calculator, because it's tedious and it's something that requires practice to get good at. And obviously, I am not as good on the calculator as you are going to need to be in order to not make any errors on your AP Calc exam. So practice, practice, practice. That's what helps you to do well. Check your answers as you go. Make sure you're getting them right. If you don't, look to see where you went wrong. And if you need help, you can always take a picture of your work and send me an email, and I will look to see what you might be doing wrong if I can. But if you're writing it down correctly, it just takes some practice sometimes getting it entered into the calculator correctly as well. All right, I wish you all the best of luck with this assignment. Please let me know if you have any questions or need any help at all, and have a fantastic day. Bye for now.